Okay, in this short little lecture, I'm just going to review ionic and covalent bonding. Okay, a lot of this we've done in class. So let's see, ionic and covalent bonding. So electrons all want to be in the lowest energy state, and the electronic configuration, which is the lowest energy state, is where the top level is either full and or the top level has 8 electrons. That's the so-called octet rule. Okay, and now what I'm calling the top level, of course, is called the valence level, and those electrons are valence electrons. So keep that in mind. The valence electrons are going to be the ones involved in bonding. Okay, so I'll put in parentheses here, bonding. Okay, so these can be the electrons involved in bonding. The other electrons, the non-valence electrons, are called core electrons. Core electrons. The core electrons are not involved in bonding. Okay, those are the ones that stay close to the nucleus. All right, so let's take a general picture of an atom. Doesn't matter what it is. And let's say we have all the levels up to here are full. These are all full up to here. Now we have the valence level. Okay, now let's look at the valence level. Suppose there's 1 electron there. Okay, what would this atom like to do? Well, one thing, to make eight electrons, right, a lowest energy state, would be you have to add 7 more electrons to make 8. Okay, that's a lot of work to add 7 electrons to make 8. Okay, so what this atom would do with valence electron is it's easier to lose this, to give this away, to give this electron away. So it wants to give away an electron. Give away an electron. If it gives it away, and we can call this element X, it doesn't matter what it is, okay? If it gives away 1 electron, then X, if you lose 1 electron, would have a charge of +1, okay? Anything that gives away electrons, if you remember, we called these metals. Metals like to give away electrons, okay? Now, if you give away 1 electron, if you give this away, then the top level is full. And so this atom would be happy. Okay. If you give away 1 electron, those are all the elements in group 1A. Okay. So you'd see hydrogen there, you'll see sodium, you'll see potassium, and you'll see rubidium. Everything in group 1A wants to have a charge of +1 because they want to give away 1 electron. Okay. All right. Now, suppose, let me erase this. Okay. Let me erase as much as I can. Well, I didn't have to erase that. I don't have to erase all of this. Okay. Okay. So now, suppose we have the valence level. Come on, come on. So here's my valence level. Okay. And now, suppose the valence level has 2 electrons. Okay. So now it has 2 electrons. 2 valence electrons. Okay, what does this guy want to do? Well, once again, this thing could add, instead of to make 8, it could add 6 electrons, right? If you add 6 electrons, you'll get 8 electrons in the top level, the valence level. Okay, well, that's one thing it do. But what's easier for this thing to do is to give away 2 electrons. So give away 2 electrons. And so element X, if you give away 2 electrons, your charge would be +2. Okay. Now everything in group 2A, we're doing the A groups, wants to be +2. Okay, so magnesium and calcium and things like that, and calcium and strontium. Okay, those all want to give away 2 electrons. And when they give away 2 electrons, then what's left is the upper level being free, being full, excuse me. Okay, and then we can continue this for one more, okay? Let me erase some of this, okay? And now we say, all right, if you have 3 valence electrons, we play the same game. Then this wants to give away 3 because instead of adding 5 electrons to make 8, it's easier to give away 3 electrons. So if you give away 3 electrons, okay, then you have a charge of +3, and this would be group 3A. So notice the number, the Roman numeral tells you how many valence electrons it has for bonding. Okay, now again, metals give away electrons. Okay, metals give away electrons. So now, we have three electrons in that orbit. Now let's say, suppose we have 4 electrons. Okay, 4 electrons there. Okay, so let's see. What do we want to do? Let's erase a couple things. Okay, that looks good. And take this out. Okie doke. So now if we have 4 electrons, okay, well, 4 is in between, half of 8. So you could either add 4 electrons to get 8, or you can eliminate 4 electrons, right? So the top level will be full. Okay. So what does it do? Well, in group 4, if you look at group 4A, you'll see there's things like carbon and silicon, okay? Well, carbon is definitely not a metal, okay? So these are nonmetals, okay? It's nonmetals, okay? So nonmetals are going to add electrons, okay? Okay, so nonmetals are going to add electrons, okay? So nonmetals take electrons. Okay, so if the valence shell has 4, then what this wants to do is add 4 more electrons. Okay, so I'm going to put 1, 2, 3, 4. So now it has 8. Now it has 8. But if you add 4 electrons, then your total charge is going to be -4. Because you added 4 more electrons, and each electron has a negative charge. So everything in group 4A for us wants to become a -4 anion. Okay, and we're going to play the same game. We'll play the same game. I'll just clean this up a little. So nonmetals are going to want to add electrons. Okay, nonmetals are going to want to add electrons. Okay, so now we're back to the valence level. There's a valence level. Okay, now if we go, let me erase a little more. So nonmetals add electrons. Okay, get rid of all this kind of stuff. Okay, that's good. So if you're in group, remember we said the Roman numeral now tells you how many valence electrons. So in group 5A, that means there's 5 valence electrons. 1, 2, 3, 4, 5. Now, what could this do? Well, it could lose 5, right? If it lost those 5, then the upper level would be full. But it's easier, right? It's easier for this thing to add 3 electrons, right? So if you add 3 electrons to make 8, 1, 2, 3, here we're going to add 3 electrons to make 8. 5 plus 3 is 8. So these things would have an extra 3 electrons, so they want to be a negative 3 charge. Okay, negative 3. And we play the same game, okay? If we go to 6A, okay, 5A has nitrogen, phosphorus, and things like that, okay? 6A, you'll see there's oxygen and sulfur. Well, again, they have 6 electrons, right? And so it wants to add 2 electrons to make 8, right? So everything here would have a negative 2 charge. Okay, so it wants to be, oxygen wants to be negative 2, add 2 electrons. Sulfur wants to add 2 electrons, and so forth. Okay, and then finally, again, to get 8, if we go to group 7, these so-called halogens, these are the halogens. Group 7A, okay, and that's fluorine and chlorine and iodine and, bromine and those kind of things. Well, again, there's 7 electrons, 7 electrons. So they want to add 1 electron to make 8. So everything in group 7A wants to have a charge of -1. Okay, it just needs 1 electron to make 8. Okay, so the metals, group 1A, 2A, and 3A, want to lose electrons, give electrons away. Group 4, 5, 6, and 7 are the nonmetals. They want to take electrons and become an anion. So metals become cations, and the nonmetals become anions. So let's write that. And this is what we call an ionic bond. Okay, so ionic bond, because you're making 2 ions. Ionic bond is between a metal and a nonmetal. Again, metals give electrons away, and nonmetals take electrons away. Okay, so these want to be cations, right? Plus, and these want to be anions, negative. And I think we've talked about this. The simple, if we go to 1A, let's look at 1A. These things want to give 1 electron. So here's sodium. And I mentioned that we had the Lewis dot structure. So the Lewis dot structure tells us the number of dots is the number of valence electrons. So if you're 1A, you have 1 dot. And now if we look at group 7, sorry. V11, 7A, okay, and if we take something like chlorine, well, 7A has 7 dots. So I'll put 1, 2, 3, 4, 5, 6, 7. So it wants 1 electron. Well, look, sodium has 1 electron it's trying to give away. So if sodium gives an electron to chlorine, now chlorine is happy. But now chlorine has an extra minus, so chlorine's really a negative ion. Chlorine is happy, but now chlorine has an extra minus, so chlorine's really a negative ion. Potassium's happy because its outer shell now is full. It got rid of that 1 electron in the top shell. So sodium, when it gives away an electron, is a +1. So you see we have +1, -1. Give 1 electron, take 1 electron. And we said when we name these things, we take the name of the cation, which is sodium in this case, and, all right, so cation, so name of cation, add it to the root of the anion, okay, and here it would be chlor. And what we do then is we add, this is naming ionic bonds, we add the ending and ending IDE. IDE. So everyone knows this is table salt and this is sodium chloride. Okay. So anything with group 1A and group 7A is going to have the same formula because this gives one electron and this takes one electron. Okay, so if I put potassium, K, with fluorine, F, well, again, this has 1 and it wants to give it to these 7 dots. Okay, so that's going to be a 7th dot. So we'd have just K, F, and this would be potassium fluoride. Okay, if we had RB, rubidium, also in group 1A, and we put it with bromine, Br, well, again, this wants to be +1 and this wants to be -1. Give one electron, take one electron, exactly matched. So this would be rubidium bromide, rubidium bromide. Okay. If we do something like this, if we go to magnesium, magnesium is in 2A. So what does that mean? Magnesium is in 2A, means it has 2 electrons it wants to give away. So magnesium and everything in group 2A wants to have a +2 charge, wants to be a +2 charged cation. Okay. And again, if I take chlorine, chlorine, remember, has 7 electrons. It's in group 7A. Right? So it needs only 1 electron. So what's this extra electron going to do? Well, if you put it with another chlorine, now the magnesium with its 2 electrons can make 2 chlorines happy. So if we wrote this like this, Mg wants to be +2, give 2 electrons. Chlorine only needs 1 electron, right? So if I put a 1 here, 1 magnesium gives 2 electrons. But now if I put a 2 here, you see 2 chlorines take each of those electrons. So if we look, 2 times 1 is +2. 2 times -1 is -2. So we should always get 0. This gives 2 electrons. This takes 2 electrons. Okay. If I did, let's do magnesium again, right? It wants to be +2, okay, because it's in group 2A. And suppose I do oxygen. Okay, oh, oxygen. Oxygen is in group 6A. So oxygen needs 2 electrons. Well, if this gives 2 electrons and this needs 2 electrons, then this is the formula, just Mg +2 O -2. You see, I just need 1 and a 1. So the formula we'd write just as Mg +2 O -2. You see, I just need 1 and a 1. So the formula we'd write just as MgO. And the name would be magnesium, the name of the cation. Take the root of the anion, ox, and add the ending IDE. Okay. If I took, I'm just going to stick with magnesium again for a second, Mg, and I wanted to put it with nitrogen. Well, nitrogen is in group 5A, right? So this needs 3 electrons. And this is +2, right? This is going to give 2 electrons. So magnesium's trying to give 2 electrons. And nitrogen says, no, 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 I need 3 electrons. So how could they ever get together? Well, if magnesium gives 6 electrons, take 3 magnesiums, and each magnesium gives 2 electrons, then this would give 6 electrons. Well, nitrogen only needs 3 electrons, but if I take 2 nitrogens, now 2 nitrogens need 6 electrons. 3 magnesiums give 6 electrons, 2 nitrogens take 6 electrons. So the formula Mg3N2 would be called magnesium. Same thing. Take the name of the cation, magnesium nitride. See, the element is nitride. Keep that in mind, nitride. Okay? And we'll do one or two more. Okey doke. Suppose I take aluminum. Aluminum is in group 3A. How do I know this? Well, it's on the periodic table. Okay, so aluminum wants to have a charge of +3, give away 3 electrons. Okay, if I put aluminum, say, with sulfur, sulfur is in group 6A. So 6 to make 8 needs 2 electrons. If sulfur adds 2 electrons, it wants to have a charge of -2. So this gives, aluminum gives 3 electrons, sulfur needs 2 electrons. Again, we do our matching, similar to a common denominator. The common denominator would be 6, right? So if I take 2 aluminums, and each aluminum gives 3 electrons, then 2 aluminum atoms give a total of 6 electrons. Well, sulfur only needs 2. So if I take 3 sulfurs, each needing 2 electrons, then this takes 6 electrons. So the correct formula would be Al2S3. And the name, once again, there's a cation, metal, non-metal, so it's ionic bonding. And the name then would be aluminum. Take the name of the cation, aluminum. Take the root of the anion, sulf, and then add the ending ide, aluminum sulfide. Okay, so on an exam, I would ask you the correct formula for aluminum sulfide. Just look at the periodic table. Okay, look at the periodic table. Okay, so I want to say a couple words now, because if we look at Al +3, O -2, N -3, F -1, Na +1, Ca -2. All these things, excuse me, pen slipped. Okay, all these things are examples of monatomic ions. Why monatomic? Monatomic. I don't know, whatever. Okay, because each of these only have one element, right? There's just nitrogen, there's just fluorine, there's just calcium, just sodium, just oxygen, right? Just aluminum. Monatomic, one atom, ions, one atom ions. Okay, so what we want to do is I'm gonna tell you, and you're gonna have to memorize these. I'll do it on the next slide. You're gonna have to memorize these because I ask them on the exams. Okay, not memorize these. I'll do it on the next slide. You're gonna have to memorize these because I ask them on the exams. Okay, not too bad. If you use them enough, you really get to learn them. Okay, and what we're gonna do is not monatomic. We're gonna do many polyatomic ions. Polyatomic ions. And the rules are going to be exactly the same. So for example, if I have whatever X is, if it's -3, and if I have Y, +3, wants to give away 3 electrons, and Y needs 2 electrons, whatever it is, then we play the same game. We make 2 times 3 and 3 times 2. Okay, so whether X and Y are monatomic ions or X and Y are polyatomic ions, excuse me, these are going to follow the same rules that we've just been learning. Okay, not so bad. So let's see some polyatomic ions. Okay, and these you're going to have to learn. They're in the book, and they should be on YouTube. Hopefully I did that on YouTube. So I'm just going to write polyatomic ions. I'll try to remember them, as many as I can. Okay. Let's look at this. OH. I'm going to put parentheses so you know the charge of this It's polyatomic because it has more than one atom, oxygen and hydrogen. This has a -1, right? So this wants to take one electron. Okay, so this would be like fluorine and chlorine in group 7. It wants to take one electron. This is called hydroxide. Okay. Let's do the positive ions before I forget. I'm going to do a couple positive ones first. H3O plus 1. So again, it says hydrogen and oxygen, so it's polyatomic. This is called hydronium. Okay, and there's one other polyatomic that's positive, NH4, and this has a +1 charge. And this is called ammonium. Ammonium. Okay, so we'll do some more negatives. C with N, -1. This is called cyanide. Now, NO2 with a -1 needs one electron. This is called nitrite. Notice the ending, not nitride. Nitride is just nitrogen. Nitrite. I'm going to underline that, okay? Nitrite. Now, NO3 -1 is called nitrate. Notice the ending. 3 oxygens. There's 3 oxygens in nitrate, 2 oxygens in nitrite. SO3 has a -2 charge. This is called sulfite. Again, notice the ending. Sulfide, IDE, is just sulfur. Okay. SO4, one more oxygen, is going to be the 8, like nitrate and nitrite. So this is going to be sulfate. Again, notice the ending. Okay. Here's a good one. CO3 has a -2 charge. This is called carbonate. MnO4, I think that's -1. This is permanganate. This is permanganate. CrO4 -2. This is called chromate. -2 means it needs 2 electrons, okay? And here's one with 3. PO4 needs 3 electrons. Look at that, needs 3 electrons. This is called phosphate. Okay, phosphate. I think, I don't know if there's anything else I want to give. Carbonate, hydroxide. Well, I can't think of anything now. Okay, so let's see how we would mix some of these. Okay, so suppose I want to make, suppose I want some calcium phosphate. As I said, you have to learn these polyatomics. Sorry. Now, calcium, you don't have to memorize. That's the periodic table. Calcium is in group 2A, so calcium wants to give away 2 electrons. Phosphate, we just said, you're going to write the parenthesis, PO4, needs 3 electrons. Well, look, it's just our 2-3 game again. Remember, 2 and 3, how do we match them? Well, the common denominator is 6, right? So each calcium wants to give 2 electrons. So if I take 3 calciums, 3 times 2, 3 calciums gives 6 electrons. One phosphate ion, PO4, needs 3 electrons. But if I take 2 phosphate ions, then 2 phosphate ions take 6 electrons. 3 calcium ions give 6 electrons. So the correct formula would be Ca3, then the parenthesis, because that tells you have 2 of these phosphate ions. There's the formula for calcium phosphate. Okay. Suppose I want the formula for ammonium sulfate. All right, well, ammonium, we just said, was NH4, and ammonium wants to give away 1 electron. Sulfate is SO4, but it needs 2 electrons. Sulfate needs 2 electrons, but ammonium can only give 1. So if I take 2 ammonium ions, with each ammonium ion giving 1 electron, then this gives 2, and all I need is 1 sulfate ion, because that'll take 2. And so we don't write the 1 when there's a parenthesis. So this would be written very simply without the parenthesis as NH4, but 2 of those, NH4, I need 2 of those, but now we only need 1 sulfate, so we can just write SO4. Okay, and that's the formula for ammonium sulfate. Okay, suppose I want aluminum cyanide. Aluminum cyanide. Well, aluminum is in group 3A. 1, 2, 3A. So aluminum wants to give away 3 electrons, so it wants to be +3. The cyanide ion we just wrote was Cn, but cyanide only needs 1 electron. But aluminum's giving 3 electrons. Cyanide only needs 1. So if I take 1 aluminum, that gives 3 electrons, then I need 3 cyanides. Each cyanide taking 1 electron from the aluminum. Okay, so the formula for aluminum cyanide would be Al, and now again the parenthesis Cn3. This would be aluminum cyanide. Okay, so the rules for the polyatomics are identical to the rules for the monatomic. You just have to match the number of electrons given with the number of electrons taken. Okay, so these are polyatomic ions. You should learn these. And all these bonds are ionic bonds because, again, you see positive, giving, positive, and negative, taking. Positive, giving, negative, taking. Positive, giving, negative, taking. Ionic bonds. Okay? When they're monatomic atoms with ionic bonds, then we have a metal and a non-metal. But the polyatomics, you can't say they're metals and non-metals. Okay? All right. I want to talk a bit about covalent bonding. Okay, I want to talk about covalent bonding. Covalent bonding. Oopsie. Covalent bonding. And on the side here, I'm going to just mention ionic bonding. Ionic bonding, remember, is between a metal bonding. Ionic bonding, remember, is between a metal and a nonmetal, if they're monatomic. But more generally, we'd say a cation and an anion. Okay, this is more general because this involves the polyatomics. And remember, this involves the give electrons and take electrons. Okay, so ionic bonding involves the giving and taking of electrons. Okay, covalent bonding is going to be between two nonmetals. And oh, it's so wonderful, covalent bonding. Why? Because covalent bond is going to involve the sharing of electrons. They share electrons, sharing of electrons. I'll just show you a quick picture, two things, okay? Suppose I have oxygen, okay? Remember, oxygen's in group 6A. How do I know that? Just look at the periodic table. That means with the Lewis dots, it's got 6 dots. 1, 2, 3, 4, 5, 6. It's not happy because it wants 2 electrons, okay? If we take another oxygen, here's another oxygen. 1, 2, 3, 4, 5, 6. Now, both oxygens are not happy. Why? Because they only have 6 electrons. But this oxygen says, you know what? I'll share my electrons with you if you share your electrons with me. So if they share 2 electrons, with each other, then the top level will be full with 8. And then they both be happy, right? So that would be an O2 molecule. And this is what we call this a double bond, but that's not important. But they're sharing electrons, okay? If we look at group 5A and look at nitrogen, nitrogen has 5 electrons. 1, 2, 3, 4, 5. Remember, nitrogen needs 8 electrons. So there's another nitrogen, 1, 2, 3. And once again, if these two nitrogens get together and they say, you know what, I need 3 electrons and you need 3 electrons, so you know what, let's share out. See, this is a triple bond. So they would share, not give and take, they share 3 electrons. Okay, that would be N2. So covalent bonding is going to involve the sharing of electrons, okay? So what we want to talk about next is naming covalent bonds, okay? Naming covalent bonds. And it's actually easier, a little easier than ionic bonds. Naming covalent bonding. Okay, and there's a hint that we actually know how to do this in a way. Okay, so what we do is we say, suppose I write this C and O, and everybody says, oh, I know what that is. That's carbon monoxide, because there's 1 oxygen. And when we have CO2, everybody says, oh, I know what that is. That's carbon dioxide. So right away, we see there's something different than with covalent, than with ionic, right? Here we tell you how many oxygens, and here we tell you how many oxygens, okay? So here in covalent bonding, we're going to have different prefixes. Oxygens, okay? So here in covalent bonding, we're going to have different prefixes. Okay, and some of these prefixes we'll be using in organic, so they're very useful. If we have 1 of something, obviously we say mono, right? Like monoxide, okay? 2, we say di. 3, we say tri. See how easy that is? 4, we say tetra. 4 is tetra. And this all the rest of this comes from the Greek, I believe, not Latin. 5 is penta, like the Pentagon in Washington has 5 sides. Pentagon. Okay. 6 is hexa. 7 is hepta with a P, hepta. That's an E, sorry. Okay. 8 is octa. 9 is nona. And 10 is going to be deca. So I'll give you examples, and then hopefully you'll see what the pattern is. Okay, it's not too bad, not too bad. Okay, so let's see. Suppose I do this. F5 BR6. Now I make these up. Okay. Now watch what I'm going to do. That's fluorine and that's bromine. We take the full name of the first element and we tell you the number. So 5, if you look here, 5 is penta. Oh, I wrote pentagon. Oh, I'm sorry. I wrote pentagon. You're probably laughing at me. That's good. Okay, I'm sorry. Okay. So 5 would be penta. So how many fluorine? We put penta. Fluorine. Notice I put the whole name, fluorine. And now we have the bromine. How many bromine? 6. 6 is hexa. So now we put hexa. And now we put the ending bromide. We take the root, brom. And then we add the ending I-D-E. Penta, fluorine, hexa, bromide. Okay, let's do N10 Cl4. Okay. Okay. Well, 10 is deca, so this is going to be deca. Nitrogen, the whole name, nitrogen. And then 4 is tetra, tetra. The root of chlorine is chlor, ide. See, that's not so bad. All right. Let's do P3I7. Okay, again, I'm just making these up. Well, 3 is tri. And then we put phosphorus, the whole name of the complete name of the first element, phosphorus. And then we use the 7 is hepta. And this would be iodide. Triphosphorus, heptaiodide. Okay, that's not too bad, I don't think. Let's do one more. Okay, let's do S3O8. Okay, well, 3 is tri, so this would be tri sulfur. 8 is octa oxide. I think that's right. Okay, 8 and then oxide. Okay, so naming covalent. I think that's right. Okay, 8 and then oxide. Okay, so naming covalents really easy, really easy. Okay, but make sure that you have 2 non-metals, right? 2 non-metals make covalent bonds. Okay, two nonmetals make covalent bonds. Okay, so we did ionic bonding, and we did covalent bonding. And everything we've done, we've really been talking about the A groups. Group 1A, 2A, 3A, 4A, 5A, 6A, 7A. 8A doesn't interact, the noble gases. 8A, the outer shell is complete, so they don't interact. Helium, neon, argon, and stuff like that. Okay, what I want to talk about right now, just briefly, and show you what I ask, are the B groups. All right, so you have 1B, whatever, 2B, or not to be, 3B, whatever the B groups are. Okay, I'm going to tell you what we need to know, okay, just for us, okay? And what we're going to do is we're going to use something called the stock system. And the stock system makes our life a lot easier, okay? The stock system tells you what the charge is. So for example, just watch this. Mercury. Okay, Mercury's symbol is Hg in the Latin. Okay, so suppose I had Mercury, you saw this formula, Mercury, and in parentheses, 1, 2, 3, Mercury sulfide. Okay, well, ide is the element. Okay, so what is this? Well, the stock system is this, telling you the stuff in parentheses. This is telling us that Mercury has a charge of +3. That's the 3, you see. Sulfide, as I'm missing an F. Boy, I don't know what's wrong. Sulfide is just S. S is in group 6A, so we know it needs 2 electrons. So this would be S with a -2. Okay, well, there's our game again. There's 3 and a 2, so each mercury gives 3 electrons. So if I take 2 mercury atoms, that gives 6 electrons. And 1 sulfur only needs 2, so I need 3 of these. So the correct formula for mercury 3 sulfide would be Hg2S3. You see? So the stock system is telling you exactly what you need. Okay. I'll stick with mercury. Suppose I wanted, no, let's do lead. Suppose I wanted lead 4 nitrate. Okay, notice the ending. Okay, so lead 4 means I have Pb, that's the symbol for lead, and this tells me it's +4. Stock system oops, I wrote a 5. Okay, I'm sorry. The stock system is telling us what the charge is. So this is +4. Okay, nitrate, if we look a couple of slides back, is the polyatomic. It's this, NO3, but it only needs 1 electron. But lead 4 is trying to give 4 electrons. So if I take 1 lead atom giving 4 electrons, then I need 4 nitrate ions because each one takes 1 electron. So the correct formula for lead 4 nitrate would be Pb NO4, NO3, sorry, NO3 4, okay? So it's NO3 is nitrate, and then put a parenthesis, and I have 4 of those, so there's the correct formula. Okay, now I want to tell you 2 special names that we're going to do, and I've seen this on the teas, and there's many special names, but I'm going to tell you 2 special names for different ions, and these I'll also ask. So let's do that, and then we'll be done with this stuff. Okay. Okay. So let's look at copper. Copper has 2 oxidation states. So this is Why am I writing an O? I'm thinking of oxidation. Ay, 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 ay. All right. Copper likes to be Cu plus 1 or Cu plus 2. Okay. And these numbers up here, these numbers are called the oxidation numbers. Okay, I'll write that out. These are the oxidation numbers. Okay. Cu plus 1, this would be called copper 1. Well, let's see, what would Cu plus 2 be called? Oh, yeah, copper 2. Well, there's nothing new there. That's just the stock system. Okay, but they also have very special names, and this is what I want to tell you about. Okay, this is also called cuprous. Cuprous. Copper 1 is cuprous, and copper 2 is cupric. Okay, so if I gave you the formula CuO, and I said, what's the name of this? What's the name? It's not copper oxide. Okay, well, what do you mean it's not copper? It is copper oxide, but that's not the complete name. Let's look. Well, if O we know is -2, then that means copper must be +2. So this one name would be copper 2 oxide. You see? Not just copper oxide, it's copper 2 oxide. Or copper 2, this would be cupric oxide. Both are exactly the same, cupric oxide. Okay, now, same thing. See, if I wrote Cu2O, and I ask you on a test, what's the name of this? Once again, it's not simply copper oxide. Okay, why? What do you mean? Well, again, oxygen we know is -2. That means this must be a +1 because 2 times 1 cancels that out. So Cu2O, so copper 2, did I say, I'm sorry, this is copper 1, sorry, see, silly. This would be copper 1 oxide because that's a +1. All right, or we would call this cuprous oxide. You see, so you can't just say I want some some copper oxide because there's cupric oxide and cuprous oxide. Okay, and if I had something like Cu3P2. And I said, what's the name of this? Well, geez, I don't know. That's hard. Okay, well, let's see. Phosphorus is in group 5A, so phosphorus wants to be -3. That means -3 times 2. This takes 6 electrons. So oxygen, copper has to give 6 electrons, so this must be a +2. So the name of this would be either copper 2 phosphide, or equally as good would be cupric phosphide. Okay, you see that? Um, if we had CuBr, and I said, what's the name of this? Well, bromine is -1, so that means this has to be +1. So this would be copper 1 bromide. And equally as good would be cuprous bromide. So if on the test, if I say, what's the correct formula for cuprous oxide, bromide, this would be it. Okay. Okay, so we have copper has two names, cupric, copper 2, or cuprous, copper 1. Okay, and there's one other example I want to do with you, and then we'll be done. Okay, and that's iron. Okay, iron has two oxidation states, Fe plus 2 and Fe plus states, Fe plus 2 and Fe plus 3. Okay, so again, this would be called iron 2. No surprise, right? The stock system. This would be called iron 3. Right? This would also be called ferrous, and the iron plus 3 is ferric. The bigger one is ferric. Okay, so if we wrote FeO, ugly in Spanish, feo, and I say, what's the name of this? Well, again, we know oxygen is -2, so this must be +2. So this would either be iron 2 oxide or ferrous oxide. Okay, ferric. Okay, if I gave you, excuse me, Fe2O3, and I said, what's the name of this? Well, once again, we know oxygen is in group 6A, so oxygen needs 2 electrons. So if it needs 2 electrons and I have 3 oxygens, that means it takes 6 electrons. So this must be a +3. So it gives 6 electrons. Well, this would be iron 3 oxide or ferric oxide. It also has another name. So those two names are equally good, but we also call this rust. So another name for rust is iron 3 oxide or ferric oxide. Okay. If I had Fe2SO3, and I put a 3 there, and I said, what's the name of this thing? I have no idea what the name of this is. Well, SO3 is sulfite, and it has the -2 charge. Okay, now 3 times 2 is 6, so this takes 6 electrons. That means this has to give 6 electrons, so this must be a +3. So one name of this would be iron 3, and this is sulfite. I hope I didn't say sulfate. It's sulfite. SO3 is sulfite. And or, equally well, iron 3 would be ferric sulfite. So on the exam, I could say, what is the correct formula for ferric sulfite? And I'd give you all different choices, Fe2, SO33, Fe3, SO32, et cetera, et cetera, et cetera. Okay? And if I gave you FePO4, and I said, what's the name of this crap? Geez, I don't know. That's hard, right? Well, what I want to do is I want to identify PO4 is the polyatomic phosphide, and it has a -3 charge. That means this iron must have a +3 charge. So this would be iron 3 phosphide, phosphate, I'm sorry, phosphate. That's the phosphate ion, polyatomic. Or we would call this ferric phosphate. This ferric phosphate. Okay. So iron 2 or ferrous, iron 3 or ferric. So remember the B group, whatever the B group stuff are, I'll always give you the stock system, right? I'll always put the number 1, 2, 3, whatever it is, or 2. I'll always put that in parentheses, and that'll tell you the charge of the cation, okay? Okay. And that's it. That's all I have to say. So ionic bonding and naming, covalent bonding and naming, and don't forget the prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, right? Remember this also, I didn't mention this. We had CO. We said that was carbon monoxide. CO2, carbon dioxide, all true. When there's one, the first one is only one element. Usually we don't say monocarbon monoxide or monocarbon dioxide. We just say carbon dioxide, right? So if I had SO3, this would not be monosulfur trioxide. It'd just be sulfur trioxide. Okay, so we don't say the mono for the first one. Okay, and I think that's all I want to say. All right, good luck. Thank you.